4.2. The mean value theorem. The outline of this video is as follows. We will discuss the deep connection between a function and its derivative. Our journey begins with an intuitive special case known as Rolle's theorem, which provides the foundation for our main result. From there, we will generalize this idea to state the mean value theorem, a more powerful principle, and I will walk through the core concept of its proof. To make the theorem concrete, we will then explore its physical and geometric interpretations, connecting it to real-world ideas like average velocity and the slopes of tangent lines. We will conclude by examining a key application: how the mean value theorem allows us to find a function if we only know its rate of change, which is a foundational concept in calculus. Let us explore two fundamental questions that connect a function to its derivative, which will guide our work in this section. We already know that a simple constant function, like y equals 5, has a derivative that is always 0 because its graph is a flat horizontal line. But could a more complicated, non-constant function also have a derivative of 0 everywhere it is defined? And for our second question, if we discover two different functions that share the exact same derivative over an interval, how must those original functions be related to each other? To build up to the answers, we will first establish a special result called Rolle's theorem, which provides an intuitive foundation for the more general mean value theorem. Understanding this connection is key, because it reveals just how much a function's derivative tells us about the function itself. Let us explore a foundational result called Rolle's theorem, which provides a simple guarantee for finding a horizontal tangent on a curve. For this theorem to apply, a function must satisfy three specific conditions. First, it must be continuous on a closed interval from a to b, which means its graph has no gaps or breaks. Second, it must be differentiable on the open interval between a and b, so the curve is smooth with no sharp corners. Finally, the function's values at the endpoints must be equal, so f of a equals f of b. If these three conditions are met, the theorem promises that there is at least one point, which we can call c, between a and b where the derivative f prime of c equals 0. Imagine driving over a smooth hill that starts and ends at the same elevation. You must have traveled on flat ground at the very top. The essential idea is that a smooth curve, starting and ending at the same height, must have at least one horizontal tangent somewhere in between. It is essential to remember that Rolle's theorem only applies if all its conditions are met. If even one fails, we cannot guarantee a horizontal tangent. The theorem requires the function to be continuous on the closed interval. If a function has a discontinuity, its graph can have a break at an endpoint or an interior point, allowing it to start and end at the same height without ever leveling off. The function must also be differentiable on the open interval. If it is not, the graph could have a sharp corner, like a V-shape. This sharp point allows the function to change direction suddenly, again avoiding any point where the tangent is horizontal and the derivative is 0. Therefore, you must always verify both the continuity and differentiability hypotheses before you can use the theorem. We can combine two powerful theorems to prove that an equation has exactly one solution, which is a common and useful technique. First, we establish the existence of a solution using the intermediate value theorem. For the function f of x equals x cubed plus 3x plus 1, we see that f of -1 is -3 and f of 0 is 1. Since the function is continuous and changes sign, it must cross the x-axis at least once. Next, we prove this solution is unique using Rolle's theorem in a proof by contradiction. Let us assume there are two roots, at x equals a and x equals b. Rolle's theorem would then require a point c between them, where the derivative is 0. However, the derivative, f prime of x, is 3x squared plus 3. Because x squared is always non-negative, the derivative is always at least 3 and can never equal 0. This contradiction proves our assumption of two roots was false, so the equation must have exactly one real solution. The main value theorem is a powerful generalization of Rolle's theorem, applying to functions that do not necessarily have the same value at their endpoints. The theorem states that if a function is continuous over a closed interval from a to b, and differentiable on the open interval between them, then a special point must exist. Specifically, there is at least one point, which we call S(x) inside the interval, where the instantaneous rate of change equals the average rate of change over the entire interval. This means that f prime of c is equal to the quantity f of b minus f of a, all divided by the quantity b minus a. Geometrically, this says the slope of the tangent line at tink is the same as the slope of the secant line connecting the endpoints. For example, if your average speed on a trip is 50 miles per hour, your speedometer must have read exactly 50 at some instant. The mean value theorem guarantees that the average rate of change across an interval is always matched by an instantaneous rate of change somewhere inside it. The proof for the mean value theorem is quite elegant because it cleverly reduces the problem to one that Rolle's theorem can solve. We start by defining a function, g of x, for the secant line that connects the two endpoints of our curve. Then, we create a new helper function, h of x, as the difference between our original function, f of x, and the secant line, g of x. You can think of h of x as the vertical gap between the curve and the secant line. Since the curve and the line meet at the endpoints, this gap is 0 at both x equals a and x equals b. This satisfies the conditions for Rolle's theorem, which guarantees a point SC where the derivative h prime of SC is 0. Because the derivative of h is simply the derivative of f minus the constant slope of the secant line, this directly proves that f prime of c must equal that slope. So the proof works by creating a new function that has a horizontal tangent exactly where the original function's tangent is parallel to its secant. The mean value theorem provides a powerful physical intuition by connecting average and instantaneous rates of change. Let us think of the term, the fraction f of b minus f of a over the quantity b minus a, as the average change of a function over an entire interval. In contrast, the derivative, f prime of c, represents the instantaneous change at a single, specific point c. The theorem guarantees that at some interior point, this instantaneous change must be exactly equal to the average change over the whole interval. For example, if a car accelerates from a stop and travels 352 feet in 8 seconds, its average velocity is 44 feet per second. The mean value theorem tells us that at some moment during that drive, the car's speedometer must have read precisely 44 feet per second. The essential takeaway is that the average rate of change over an interval is always achieved instantaneously at some point within it. Let us explore the first important consequence of the Melian value theorem, which shows that only constant functions can have a derivative of 0 over an entire interval. To understand this, imagine picking any 2 points, x1 and x2, within that interval. The mean value theorem guarantees there is some point c between them, where the instantaneous rate of change, f prime of c, equals the average rate of change between our 2 points. But our starting condition is that the derivative is 0 everywhere, so prime of c must be 0. This forces the average rate of change to also be 0, which means the function's value at x1 must equal its value at x2. For instance, if a car's velocity is always 0, its position must be constant. The key takeaway is that a function whose derivative is 0 everywhere on an interval cannot be changing at all. It must be constant. Now we will explore a crucial consequence of our last result, which is that if 2 functions share the same derivative over an interval, they must differ only by a constant. To see why this is true, imagine 2 functions, f of x and g of x, where f prime of x equals g prime of x. If we define a new function as their difference, h of x equals f of x minus g of x, then its derivative, h prime of x, must be 0 everywhere in that interval. From our previous corollary, we know that a function with a 0 derivative must be a constant, which we can call c. This means that f of x equals g of x plus c. For instance, many functions have a derivative of 2x, but they all must be of the form x squared plus some constant, representing a family of vertically shifted parabolas. This principle is the foundation for finding antiderivatives, a process we also call integration. We can now apply our corollary to solve a common problem, finding a specific function when we know its derivative and a single point on its graph. First, we need a general solution for a function whose derivative is sine of x. Since we know the derivative of negative cosine of x is sine of x, our corollary tells us that any such function must have the form f of x equals negative cosine of x plus some constant, c. This equation represents an entire family of functions. To find our specific function, we use the initial condition that the graph passes through the point 0, 2. We set f of 0 equal to 2, which gives us the equation negative cosine of 0 plus c equals 2. Since cosine of 0 is 1, this simplifies to negative 1 plus c equals 2, which means the constant c must be 3. Therefore, the unique function that satisfies both conditions is f of x equals negative cosine of x plus 3. Knowing the derivative gives a family of curves, but one point pins down the specific curve. We can use the same derivative principle to prove the laws of logarithms, starting with the product rule. To do this, I will compare two functions. F of x equals the natural log of the quantity b times x, and g of x equals the natural log of x. Using the chain rule, the derivative of f of x is 1 over the quantity b times x multiplied by b, which simplifies to 1 over x. The derivative of g of x is also 1 over x. Since both functions have the same derivative, we know they must differ by a constant value, c, so the natural log of b times x equals the natural log of x plus c. To find this constant, we can plug in a convenient value like x equals 1. This gives us the natural log of b equals the natural log of 1 plus c. Because the natural log of 1 is 0, we find that the constant c must be the natural log of b. Substituting this back proves the familiar rule. The natural log of bx equals the natural log of x plus the natural log of b. This summary connects our key theorems, showing how they build upon one another to form a powerful logical chain. We began with Rolle's theorem, which is the specific case ensuring a horizontal tangent exists when a function's start and endpoints share the same value. The mean value theorem then generalizes this idea, guaranteeing that for any differentiable function, there is always a point where the instantaneous rate of change perfectly matches the average rate of change over an interval. From this, two critical corollaries follow. First, a function whose derivative is always 0 must be a constant. Building on that, the second corollary shows that if two functions have the identical derivative, they can only differ by a constant value. This final insight provides the rigorous foundation for anti-differentiation, the process of reversing differentiation that is central to calculus. Let us conclude by applying these ideas to a couple of practical problems to check our understanding. First, consider a trucker who covers a known distance in a specific amount of time, resulting in an average speed that is above the speed limit. I want you to think about how you would use the mean value theorem to justify a speeding ticket by connecting this average speed over the whole trip to the trucker's instantaneous speed at a specific moment. For the second question, imagine we know a function's derivative is 2x, and we also know its graph passes through the point 1, 0. You can use our corollary about functions with the same derivative to first find the general family of functions, and then use the specific point to solve for the constant and find the exact formula. These examples show how the theorem let us link average and instantaneous rates and even reconstruct a function from its rate of change.